Welcome to Cheenta School of Statistics and Data Science. Today we will be doing the problem from GATE 2022 Statistics paper, the question number 13. The problem says that to check a square, whether a square is an unbiased estimator of sigma square and S is an unbiased estimator of sigma, where A square is the sample variance. The sample is drawn from the normal population with unknown mean mu and unknown finite variance sigma square is greater than 0. So here, the population is a normal mu sigma square, and mu sigma is unknown sigma square is greater than 0. We have drawn the random sample x1, x2 up to xn from the population. So each xi is an IID normal mu sigma square random variable from the property of random sample. So here, expectation of each xi is mu and variance of each xi is sigma square. So we are going to start the part 1. So here a square is given by the formula 1 by n minus 1 I equal to 1 to n xi minus x by x bar whole square. So we have to check whether expectation of a square is sigma square. So for sophisticated way of writing, we consider n minus 1 into a square and take its expectation. The expected value of this is coming out to be n minus 1 into sigma square. Here, how it is came, let's see. So we first expand the xi minus x bar whole square. So by expanding it becomes summation xi square minus 2x bar. As x bar is independent of I, it comes out of the summation value, and summation xi plus n x bar square. Again, x bar is the constant, so it comes out of the summation. Now, as expectation is a linear function, it go inside the summation value, and here is the expectation of xi square minus expectation of x bar square. Here summation xi can be written as n x bar. We have put the value and we got 2n expectation of x bar whole square plus n into expectation of x bar whole square. Now expectation of xi whole square minus expectation of xi whole square is variance of xi. So we can write expectation of xi square equal to variance of xi, which is sigma square, plus expectation of xi whole square, which is mu square for all I. So in this procedure, we can also obtain expectation of x bar is mu and variance of x bar is sigma square by n. So we now plug in the values. Expectation of x square is mu square plus sigma square. It is coming out of the summation value with the constant multiplied n, and it becomes expectation of x bar squared, which becomes variance of x bar plus expectation of x bar whole square. So by manipulation, we got that expectation of n minus 1 into a square is n minus 1 into sigma square. So a square, expectation of a square is coming out to be sigma square. So we can say that a square is an unbiased estimator of sigma square. Now to check whether S is an unbiased estimator of sigma, we have the information that variance of any quantity is greater than 0. We have use that for S, or sample standard deviation. So expectation of a square minus expectation of s whole square is greater than 0. So expectation of a square is sigma square. We just obtained that, and expectation of s whole square is coming out to be less than sigma square. Now from this we can conclude that expectation of s is sigma, because s is a positive random variable. It is sample standard deviation, and hence expectation of s should be greater than 0, because expectation lies within the support or the domain in which the random variable takes values. So we have got that expectation of a square is sigma square indeed, but expectation of s is not equal to sigma. Hence, we obtain that 2 is not correct. Okay. Now next to the part 2. So here we have to find, let us check the problem once. Here we have to check whether n minus 1 by n square is a maximum likelihood estimator of sigma square, and similarly the case of standard deviation. So for this, we obtain the likelihood function. So given the sample x curl, we write the likelihood function of the parameters mu sigma as L mu sigma given x. So this is the product of the PDF. So by taking the derivatives, we can obtain the solutions of the extreme points. That is the point at which the this function will be maximum or minimum. Let's see. So we can take del L del mu equal to 0 and del L del sigma equal to 0, and then get a solution. But a more sophisticated way would be to take the logarithm of the likelihood function. We denote it by small l, and that is coming out to be constant minus some n ln sigma. Ln is log base e minus half into summation I equal to 1 to n xi minus mu whole square divided by sigma square. So by taking the derivative and both derivatives and equal it to 0, we get the solutions as by simultaneously solving, we get the solutions as mu hat equal to x bar, and putting the value of mu hat in the equation 2, we get the solution of sigma hat square is n minus 1 by n s square. So now we have a property, invariance property for maximum likelihood estimators. So if t, a statistic, is an maximum likelihood estimator of some parameter theta, unknown parameter theta, then gt is also a MLE of g theta, provided g from real to real valued function of theta. So if g is a function of theta, then only gt is a maximum likelihood estimator of g theta. So now we have n minus 1 by n square is the MLE of sigma square, and hence we take g theta is root theta, and it is a function of theta, real valued function of theta. So root over of g theta, root over of n minus 1, that is g here, t is n minus 1 by n square. So root t, it is MLE of sigma square. So root t is also MLE of sigma. So here root t is coming out to be a root over n minus 1 by n into s. So by the invariance property, we can say that root over of n minus 1 by s is the MLE of sigma. So we can see that n minus 1 by n square is MLE of sigma square, and n minus 1 by n root into s is sigma, MLE of sigma also. So hence 2 is correct. So we check that only 2 is correct. This is all for today. Thank you for watching. We will see you in the next video. Stay blessed. Thank you.